So we're in our logarithm and exponential unit. They go hand in hand, as you will find out. So exponentials and logarithms are actually inverses of each other. So today we're focusing on exponentials, and then next time we'll get into logarithms. You have to understand how exponentials work really well to be able to understand more easily how logarithms work. So first of all, exponential functions have this form: a times b raised to the x, where a is what's called our quote-unquote initial value, or our starting point. That's where we're starting. And then b is our growth or decay factor. Growth will be if it's larger than 1, from left to right, it's growing exponentially. So for example, a 2 would be larger than 1, so that would be exponential growth. If it's decay, that just means it's getting exponentially smaller from left to right. So if b was a half, that means from left to right it starts out large and gets smaller and smaller. Does that kind of make sense, everyone? Okay, so now looking at this, f of x is equal to 2 raised to the x. A lot of people get confused with what the initial value is versus what the growth factor is. So I want to point something out. Our initial value is not raised to the x. The growth factor is what's raised to the x. So in this one, our initial value is a 1. Even though it's not there, it is a 1. Does everybody see? Because the 2 part is raised to the x. That's our growth factor. So because 2 is greater than 1, this is growth. So you're going to see from left to right, it's going to start small and get exponentially larger. Now we're going to just plot some points here. So let's start with 0. 2 to the 0 power is 1. Perfect. Let's plot that point. Over 0 up 1 unit. Check. Now if I plug in 1, 2 to the first power is 2. So over 1 up 2 units. Now let's plug in one more. If I plug in 2, I get 4. So over 2 up 4 units. Now we could keep going. Obviously, if I plug in 3, I get out 8. So just because it can fit on my graph, there it is. And then let's start plugging in some negatives. Like let's plug in -1. Now careful, because 2 to the -1 is not -2. 2 to the -1, by definition, with negative exponents, we flip it, don't we? Over a fraction. So 2 to the -1 is 1/2, everybody. Not negative, it's 1/2. So we're going -1 up a half unit. Now let's plug in a -2. So look, 2 raised to the -2. Wouldn't that be 1 over 2 squared? Which would be 1/4, because it gets flipped. So now notice it's just getting smaller. It's not getting negative, it's just getting really, really small. That, by definition, is creating an asymptote. No matter what value we plug in the negative direction, isn't it just going to get smaller and smaller? That's approaching 0. So if we connect these dots here, there's our exponential growth. Notice from left to right, it started out really, really small, and then it got exponentially larger from left to right. And we have what's called a horizontal asymptote at y equals 0, because there's no way it could ever be negative. No matter what you plug in, it's just going to be a smaller fraction. So that we have to draw in our horizontal asymptotes. All exponential functions will have a horizontal asymptote at 0 until we start shifting. That will shift our horizontal asymptote. Great. So what would my domain be on this one? Where is it growing from left to right? Negative infinity to infinity. Good. So negative infinity to infinity is our domain. And our range is the y values. Didn't we just say it isn't negative? So it starts at 0 and then goes to infinity. Not including 0, because it's an asymptote. It's just approaching it. Does that make sense? 0 to infinity, parenthesis, not including 0. Okay, let's do a decay one, an exponential decay. So right here, notice, 1/2 is less than 1, making it decay. So let's just plug in values. So if I plug in 0, I get a 1, don't I? Now notice they both started at 1. You see, 1, 1. That makes sense, because any base to the 0 power is going to be 1. If I plug in a 1, I get a 1/2. So over 1 up a half unit. If I plug in a 2, guys, look, 1/2 squared, you'd square the top, square the bottom. That'd be 1/4. So it's just getting smaller and smaller. So now it's over 2 up only a teeny bit. So no matter what I plug in, if I plug in a 3, I get an 8. I'm just getting smaller and smaller. So I'm approaching my asymptote again. Now let's plug in a -1. Watch, 1/2 raised to the -1 power. That would be 1 to the negative 1 divided by 2 to the negative 1. Don't we flip negative exponents? So that's going to be 2 over 1. So it just flips it. It's now 2. When I plug in a negative 1, I get out 2. Does everybody see? Flip the fraction. So negative 1 up 2 units. If I plug in negative 2, what am I going to have? 4. Yep, 4. So negative 2 up 4 units. Great. If I plug in negative 3, I'll get 8, won't I? Flip it. Okay, awesome. So now look, that I can see that it's decay. From left to right, it started out really large, and it got exponentially smaller from left to right. And then we would draw in our horizontal asymptote at 0. So our domain would still be negative infinity to infinity, and our range would be still 0 to infinity, wouldn't it? Not including 0, because it just approaches our asymptote, not negative. So here are some key features. No matter what, if we have a growth function or decay function, if it has the form y equals, okay, if it has the form y equals base a to the x, we just saw that the domain will always be negative infinity to infinity, won't it? Think about all exponential functions. They all look like this. It'll always point this way forever and this way forever. The domain will always, for all exponentials, be negative infinity to infinity. Even if I start shifting this around, it's going to still point this way forever and that way forever. Even if I move it clear over here, it's still going to point this way and this way forever. Left and right forever. Our range will be 0 to infinity if there's no shift. If it has the form y is equal to base a raised to the x, it'll always be 0 to infinity. So we will always have a horizontal asymptote at y equals 0 if it has that form. Now our y-intercept, where it crosses the y-axis, is always when x equals 0. So no matter what, think about it. If I plug in 0, I'm going to get a 1, right? 0, 1. So that will always happen. And then it says that these points will always be on the graph, 1, comma, a. Well, let's make sense of y. If I plug in a 1 here, won't it be a out, the base? 3 to the 1. If I plug in 1, I'm going to get out the base 3. Do you guys see why they're saying that point will always be on the graph? And then let's plug in a negative 1. 3 to the negative 1 is not negative 3, it's 1/3. So they're saying that the point negative 1, comma, 1 over a will always be on the graph. But we don't have to memorize that. We're just going to plug in points and it will happen anyways. Okay, just kind of things to see. Okay, let's graph a couple more. So, once again, the first thing you would do is say, okay, it's kind of nice to know if it's growth or decay, because then you can kind of see if you're graphing it right. Isn't this one decay? A fourth is less than 1, so it's decay. So then from left to right, it's going to start large and get exponentially smaller. You're going to make an XY chart. Let's start with 0. 1/4 of the 0 power is 1. Okay, let's plug in a 1. We get a... Plug in a 1. We get a 1/4. If I plug in 2, I get 1/16. Well, I'm not going to plug. It's just getting smaller and smaller. I'm going to stop there. Let's plug in a negative 1. 1/4 to the negative 1 is 4. We flip it. So that's 4. Now, if I plug in a negative 2, I'm going to not get 8. I'm going to get 16, aren't I? So, okay, let's say I wanted to put it just for kicks and giggles. Okay, let's start plotting those points. But even before plotting those points, where's my horizontal asymptote going to be at? 0. So I actually will just draw that in first. All right, here we go, plotting points. So we're going over 0 up 1 unit, check. Over 1 up a 4th unit, so up barely any. Over 2 up, it's just approaching this asymptote, so it's just getting smaller and smaller. Then over negative 1 up 4 units. Then over negative 2 up 16, so clear up there. So when I draw it, I can't be messy. I can't go, because then it looks like negative 2 crosses over here, but it doesn't, right? It crosses clear at 16. Do you guys understand that? So you got to graph it pretty appropriately. It goes up quite quickly. And then it's just approaching our asymptote. My domain would be negative infinity to infinity. My range would be 0 to infinity. Good. Now look, from left to right, it was large and got exponentially smaller, didn't it? Decay. We always write the smallest one first. But you guys see how from left to right it was large and got exponentially smaller? Decay. Yeah. Because negative exponents means you flip your fraction. That's just by definition what a negative exponent is. So 1/4 raised to the -1 would flip both of those. That would be 4 over 1. Okay, another one. Let's graph another one. This one is growth. Because 4 is greater than 1. So now we'll just make an XY chart. Once again, we'd say if I plug in 0, I get 1. If I plug in 1, I get 4, don't I? If I plug in 2, I get 16. Good, that's not on the graph, but whatever, that's fine. We can have some extra points there. If I plug in -1, you don't get -4, you get 1/4. Okay, so it's just getting smaller and smaller. So now I would go drawing my horizontal asymptote at 0, and then I would start plotting points. Over 0 up 1, over 1 up 4, over 2 clear up at 16. Great, that's getting larger than over -1 up a 4th. By definition, we know it's going to approach the asymptote and it's going to go up exponentially. So look, from left to right, it started small and got exponentially larger. So that's why it's growth. Our domain would still be -infinity to infinity, and our range would be 0 to infinity. Not including 0, because an asymptote is a value that your function approaches, not is equal to. Okay, awesome. Pretty good, easy stuff. So let's now take and start shifting this. Now think about it. If I take this function that we're at and I start shifting it, let's picture myself shifting this a couple units this way. If I do that, it would look something like this. Does that change the domain and range? No, it's still going this way and this way forever. So it'd still be -infinity to infinity. So shifts left and right do not affect your domain. It's still -infinity to infinity. It'll always be that for exponentials. But now let's say I shifted it up 3 units. That would take this asymptote, and it would be really important to us because now if we shift it up 3 units, our new asymptote would be up at 3. So now it would be up here. Does that make sense, everyone? So now our range would be 3 to infinity. Shifting for all functions works the same, so we don't need to learn anything new. Shifts left and right are grouped in with x. We go opposite. Shifts up and down are added on the outside. So in words, describe the shift. Right 1. We know how to shift all functions by now. We've done it in Sec 3 and we've done it in here all year. Are we good? Right 1. Shifts left and right, you go opposite. It's grouped in with x. This is a shift of up 2. The first thing I do with something like this is draw my new asymptote. What is important? Not the shift left and right, but the up 2, correct? It used to be at 0, so now it's up at 2. I would draw in my horizontal asymptote. Now from here, everybody listen to what I'm about to tell you. You are then going to write down the parent function, the non-shifted function. You're going to make a table of values for the parent function. Do it this way. So you're going to say y is equal to base 2 to the x is the parent function of this, because that would be the function with no shifts. You're going to plot those points. So in this xy chart here, I'm writing down my parent function points. Let's plug in a 0. What do I get? 1. 2 to the 0 power is 1. Does everybody understand? Plug in a 1, I get 2. Plug in a 2, I get 4. Plug in a -1, don't I get a half? If I wanted, I could plug in a -2, I get a 4th. That's good enough. That's plenty of points here, isn't it? Now from here, we're literally just going to take our xy points and shift them. Right 1 means you take your x's and add 1 to them, wouldn't you? Then your y values, it says up 2, you're going to take and add 2. So now for this function, you have your exact xy points to graph, and it's really straightforward. So -1 plus 1 is 0, right? 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. Check. A half plus 2 is, let's just do decimals, 2.5. It's easier to graph decimals. 1 plus 2 is 3. 2 plus 2 is 4. 4 plus 2 is 6, right? So now all you have to do is plot those points, and it will hug your asymptote. You'll see that it'll all work out. So over 0, up 1, 2.5 units. Boom. Over 1, up 1, 2, 3 units. Check. Over 2, up 4 units. Over 3, up 6 units. Can I see it now? Yeah, because we know it's approaching an asymptote, right? We know what these exponential graphs look like. We see it coming up like this, right? and then it's going to approach the asymptote, like that. So we would draw arrows. Now it's easy. We'd say our domain is negative infinity to infinity, isn't it? Our range is 2 to infinity. Look, that is, we could know the range without even graphing it, 2 to infinity. So our range is 2 to infinity, not including 2, because an asymptote is a value it approaches but doesn't usually cross it. When I say usually, it's because sometimes in other types, never for exponentials will it cross horizontal asymptotes, but there are times in other types of functions where it can cross a horizontal asymptote, but even if it did cross, it would then hug it underneath. Yes? Yeah, that is like our new 0, essentially, yes. Great question. So these points, you're going to go off of your normal xy axis. These are official points that we're just graphing from the normal xy axis. That's what's so nice, is I used to teach this as, now treat this and do it, but then it was a lot harder. This is foolproof because you just go and plot points right on the graph, exactly as you see it. Here's my x-axis, y-axis. So it'll still just be your normal xy axis. Great question. Awesome. It was up 2 units though, right? So as you can see, our asymptote used to be at 0, it's now up at 2. No. It was a y shift of 2, so all of our y values are what shifted up 2 units. Our shifts left and we shifted right 1, but our points, so we added 1 to them, so it was all good to go. Those have been shifted right 1, even if you can't see it very good. But it all works out. Let's do another one. Okay, let's do this one. Here we go. So, f of x is equal to 3 raised to the x plus 1. In words, describe a shift. Up 1, that's the important one to us. Just left and right don't affect our, we will use it, but it's not going to affect our asymptote. So up 1 would make our new horizontal asymptote at 1. I always draw that in first. Then remember, what was my next step? To write down the parent function, which means the non-shifted function, which would be 3 to the x. Write down these x, y points. Plug in a 0, I get 1. Plug in a 1, I get 3. Plug in a 2, I get 9. That's enough points on the positive end. If I plug in negative 1, 3 to the negative 1 is 1/3, isn't it? 1/3. And then if you wanted, you could do negative 2, that's 1/9. But really, that's plenty and plenty of points because we know how asymptotes work. So then from there, you'd say no shifts left and right, so we don't have to change our x's. But we are going up 1. So you take your y values and add 1. So add 1, add 1, add 1, add 1, add 1. So our new x, y points are x's. So for this function, our x, y points are still at negative 2, negative 1, 0, 1, and 2. And now we have 1 plus a 9th, everyone, which is just a decimal. You can do a decimal. Decimals are easier to plot. So 1 and a little more. So 1 point something. Now, right here we have 1 plus a 1/3, that's about 1.3. You could do it in your calculator if you didn't know that. You understand that, right? Okay, now 1 plus 1 is 2. 3 plus 1 is 4. 9 plus 1 is 10. And now you're physically, literally just plotting those points on our normal XY chart. These points will approach your asymptote, as is. So you're going to go negative 2 up 1 and a teeny bit, right? Over negative 1, up 1 1/3, up a teeny bit. Over 0 up 2 units. Over 1 up 4 units. So look, over 1 up 4 units. And then over 2 up 10 units. And now I can see what's happening. It's approaching this asymptote right here. And it's going up exponentially. Now look, this was growth. From left to right, it grew, didn't it? It's all looking good. So our domain was negative infinity to infinity. Our range is 1 to infinity, which makes sense because it was up 1, 1 to infinity. Pretty easy if you do it the way I teach you. Okay. Okay, do you want to do one with decay and shifting? Okay, sure, let's do it. Okay, so first of all, you would say right 2, wouldn't you? Then down 3, that's the important part to us. So down at -3, I'm going to draw in my horizontal asymptote. Then from there, what was my step? Parent function, which is 1/2 raised to the x's xy points. So then from there, you'd say, if I plug in 0, I get a half. If I plug in 1, no, I don't. If I plug in 0, what do I get? 1, not a half. If I plug in 0, I get a 1. If I plug in 1, I get a half. If I plug in -1, what will I get? 2. Okay, let's say you wanted to do more points. If I plug in 2, I'll get 1/4. If I plug in -2, I'll get 4. Okay, good. There's your parent function points. Let's create the shifts now. Right 2 means we would add 2 to our x's, and then down 3 means we'll subtract 3. So these ones, xy points, are officially this. -2 plus 2 is? -1 plus 2 is 1. 0 plus 2 is 2, right? 1 plus 2 is 3. 2 plus 2 is 4. Great, there's our new x points. 4 minus 3 is 1. 2 minus 3 is -1. 1 minus 3 is -2, isn't it? A half minus 3. Now I have somebody in my early morning say, how do you get that so quick? If you need to, you can type it into your calculator, right, everyone? So a half minus 3 is about -2.5, isn't it? If you didn't know that, that's okay, type it into your calculator. And then you could do -3 plus a fourth, so that'd be -2.75. So now, great, let's plot those points. So you start at your origin. Over 0 up 1 is a point, great. Over 1 down 1 is a point. Over 2 down 2 units is a point. It's all looking good because look, it's approaching our asymptote. Over 3 down 1, 2 and a little bit. And over 4 and down 2 and a little bit. So it's approaching the asymptote. I can see what's happening here. So it's coming down and approaching our asymptote. And it's getting exponentially larger, isn't it? So our domain would be -infinity to infinity. And our range, we could have been told without a graph. -3 to infinity. Sweet. Now let's throw a wrench into it. Let's say I take now and I put a negative in front. What would that do? What kind of, yeah, it's a reflection. So just take these points and reflect them. So we would take all of our y values and times them by -1. So let's look at one like that. Because order matters. So it'll be quick. So it'll be really quick here. So you'd say, okay, so we're shifting up 4. So my new asymptote is at +4. Now from here you'd say this is a reflection over x. So then from there you'd make your xy chart for your parent function. 2 to the x. Plug in a 0, you get 1. Plug in a 1, you get 2. Plug in 2, you get 4. Plug in -1, you get a half. Plug in -2, you get 4. So then you take that, it says reflection over x. If you guys can recall, that would take all of your so take all your points and reflect them over the x-axis. That would change your y's, wouldn't it? To opposite. You got to do multiplication first. So you take your y values, we're going to times them by -1. Then after that, we're going to add 4. So this one's xy points will be as follows. Our x's didn't change. -2, -1, 0, 1, and 2. But now we're doing a fourth times -1. Isn't that -1/4? -1/4 plus 4. So that would be 3.75. A half times -1 is -1/2. -1/2 plus 4 is 3.5. 1 times -1 is -1. -1 plus 4 is 3. 2 times -1 is -2. -2 plus 4 is 2. 4 times -1 is -4 plus 4 is 0. And now I'm just plotting points. So we're up -2 and then we're up 1, 2, 3 and a little bit. We're at -1 up 1, 2, 3 and a half. We're at 0 up 3. We're at 1 up 2. And then we're at 2 up 0. Can we see it happening? You can see what's happening now. It's coming up and approaching the asymptote. And it's coming down and getting exponentially larger, but in the negative direction. So now look, that does change our range. Our domain is still -infinity to infinity. Still growing left and right forever. Our range, though, is negative infinity up to 4. So now because of the negative, it was not growing to positive infinity, it was growing to negative infinity, and then up 4 took our horizontal asymptote up to 4. So now it would be negative infinity up to 4. Okay, so now hopefully that'll be the end of our graphing. Hopefully you can see the domain and range without even having to graph it if asked. Okay, we're now going to look at a special exponential function. This will take us 1 second. It's called e. Y is equal to e to the x. People, this is just an exponential function like anything we just saw. It's just a, quote, special exponential function. People think that e is a variable, but it's not. So in real-world situations, as people were doing a lot of calculation for like investments of money and stuff, they kept running into this decimal that kept showing up over and over again in real-world situations. It's a decimal that's approximately 2.7. This decimal just kept showing up, and that's how much growth they were getting. Isn't 2.7 larger than 1? So they just kept seeing this happen in real-world situations, and it happened so much that they gave it a special little variable. But it's not a variable, so they just called it e, because it happens so much. So e is approximately 2.7. So anybody who has an e button on your calculator, great. If you don't, you're going to have to know that it's 2.7 approximately. So let's graph e. So let's plug in 0. Any base to the 0 power is 1. So over 0 up 1. Now if I plug in a 1, e to the first, you can type it into your calculator, those of you that have an e button, but even if you don't. Isn't it about 2.7? 2.7 to the first is about, isn't it 2.7, guys? And if I plug in negative 1, that's not negative 2.7. 2.7 to the negative 1 is 1 over 2.7. Isn't that just a small decimal? So that's just 1 over 2.7 is a really small decimal. So we're going negative 1 up a teeny bit. Okay. And then over 1 up about 2.7. So it's exponential growth, looking like this. So our asymptote is still just like all the other exponential functions at 0. You guys see how it's just a growth factor of 2.7. Our domain would be negative infinity to infinity, just like all our other exponential functions, and our range would be 0 to infinity. So now what if I shifted the e function? It would be no different than shifting our other exponentials. So I'm going to ask you, what is the domain and range of this e function? So it's shifted left 2. Will that change the fact that my domain is growing left and right forever? No, all exponential functions have a domain of negative infinity to infinity, so don't be mistaken. Our range, however, used to have an asymptote at 0. It's now at negative 3, isn't it? Isn't it facing upward still because it wasn't reflected? So you'd say negative 3 to infinity is my range. Do we have any questions on that? Let's look at one more, then we'll be done with graphing. State the domain and range of this one. Try this one by yourself. What's the domain and range? Okay, what's the domain? Negative infinity to infinity. That does not change for exponential functions, no matter what. Okay, what's my range though? Negative infinity up to 5. Do you all agree? Do you need me to answer why that is? Reflected, so now it's going down, right? And it's up to 5. Okay, awesome. Good. Alright, so now we're doing the fun stuff. Evaluate with the calculator. Take your calculator, type it in. It's that easy. It says, what is 3 raised to the 1.4? So you literally just type in. 3 raised to the 1.4 is 4.655536722. Not hard, is it? Yes. Great, right? Easy. Your calculator will still do it. You have to just borrow one of my notes. 3 raised to 1.41 is 4.706965002. Easy, right? If I said evaluate, great, I can do that. Type it in. Yeah. You still need to use non-graphing. You can use these kinds. Yep, that's why I got them. Okay, writing this down. Solving, these these are when it gets fun. I love solving equations, okay? So solving exponential equations. Now what we're doing is we're going to see a value for x. We're going to find a value for x that will make this a true statement. So these are the steps we take. First, get the base to be the same on both sides by rewriting the equations if necessary. So notice on this side I have a base 2. We need this side to be written as base 2. That's going to allow us to solve this very easily. So that's our first step. And then second, we can just solve using the exponents. So everybody, 2 raised to the x minus 3 is great. We have a base 2. We need this to be base 2. So let's say you don't know. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. And 2 to the fifth is 32. Do you guys see how 32 is equivalent to 2 to the fifth? So rewrite them as the same base. So we have 2 raised to the x minus 3 is equivalent to 2 raised to the fifth power. And now think about it. If we're trying to make this a true statement, isn't the base already the same? So what matters? Making the exponents the same, right? That would make it a true statement. So now couldn't we just say, when is x minus 3 equal to 5? You guys see how that's our true statement? That will make it be the same statement. So then, add 3 over. So x equals 8. Look, that makes it a true statement. 2 to the 5th equals 2 to the 5th. You guys see? So we just solved using the exponents. Now if you take and go up here, plugging in 8, 2, 8 minus 3 is 5, 2 to the 5th is 32. You see how you can check your answer? Easy, right? Get them as the same base, solve with the exponents. Do another one. 5, x minus 4 equals 5 to the negative 1. Are they already the same base? So what would my true statement be? X minus 4 equals negative 1, so then add 4. So x equals 3. Done. Moving on. This one, base 3 raised to the x plus 2. 81 is base 3 to the what power? If you didn't know, you'd start testing out. Through the first, second, third, fourth, fifth. What? Thank you. So this is also the same thing as 3 to the fourth. So we have 3 to the x plus 2 equals 3 to the fourth power. So our true statement is x plus 2 equals 4. So now we can just solve for x. So x equals 2. X equals 2, right? Now they're not always going to be that straightforward. So these have been easily written as the same base. Base 3, this could be written as base 3. But let's look at one where that is not the case. So we have right now base 4, x squared equals 32. Now 4, let me show you. 4 to the first power equals 4. 4 to the second power equals 16. What's 4 to the third power? 64. Do you guys see how we cannot write this as a base 4? If that happens, then there's a different base that we should be using, not base 4. So you would go to your smaller base and say, what can I rewrite this as a different base? Base 2. Isn't that the only one? Base 2 to the what power equals 4? Base 2 squared. So we're going to say, okay, so 4 is equivalent to 2 squared. So 2 squared x squared. You guys see how those are the same thing? So now it's written as base 2. Can we write 32 as base 2? Isn't it 2 to the 5th equals 32? So now on this side, we can write that as 2 to the 5th. So our true statement is this. 2 squared raised to the x squared equals 2 to the 5th power. Does everybody see? Now you got to be really careful here, because actually, what are we actually looking at? Raise a power to a power and you multiply. So we're actually looking at base 2 raised to the 2x squared equals 2 to the 5th. And now we have both base 2's and we can solve with our exponents. So now you'd say my true statement is 2x squared equals 5. Solve for x. So what would we do first? Divide by 2. X squared equals 5 halves. Then what? Square root both sides, not forgetting a plus or minus. Then I need to split it up, don't I? Is that answer an appropriate answer? No, we would then rationalize our denominator. We'd multiply by root 2, root 2. So our final answer is x is equal to plus and minus root 10 all over what? 2. Okay, let's look at another one of similar difficulty level. Okay, so we have base E, and equals E. They are all the same base, aren't they? But the problem is we need it to be one base. Can anyone think of how we can rewrite this left side as one base? Good thought. Yes, you're saying when you divide the same base, you subtract. So he's saying I have the same base. I know that I can put the bases together with properties of exponents and use subtraction. Way to remember that. So you're saying that we have base E, the top minus the bottom, so that'd be x squared minus 2x is an equivalent statement to this. Yes, guys, that's properties of exponents. By definition, they are equal. So equals e to the 8th. And now we have one base, so we can now set up our 2 statement. Way to remember that. So we have x squared minus 2x equals 8. So now from there you'd say, okay, to solve a quadratic, I always get it set equal to 0. So we'll have our x squared minus 2x minus 8 equals 0. Then we'll solve by factoring if possible. Most of these will factor. We'll multiply to be negative 8, adds it to be negative 2. 4 times 2, negative 4. Quick factors, yes. X minus 4, x plus 2. So my 2 solutions are x equals 4 and x equals negative 2. There's our 2 solutions. Awesome. Okay, so let's see how we would set this one up. Base E, and all of a sudden we have 2 bases. That's a problem. So we have e to the x squared is equal to what? E to the 4x squared is what I'm hearing, which is a good thought, but that's a mistake that they count on you making. Yeah, when you multiply the same base, you add. So you're right, it'll be x plus 4x. So now our truth statement is x squared equals x plus 4x. Can we actually combine those? So equals 5x. Now from here, could I square root it? No, that was a trick question. You can't. What would we need to do? Subtract 5x, because to solve quadratics, we get it set equal to 0 and factor it. Good. So we have x squared minus 5x equals 0. We wouldn't do a times c in this one. What would we factor out? X, so then left is x minus 5. So we have 2 solutions. X equals 0 and x equals 5. There's our 2 solutions that would make it a true statement. All right, doing good. Okay, let's see if you can think of a way to rewrite this all as base 2. You're on the right track. Yeah? So she just said 8 is the same thing as 2 to the 3rd. Do you agree with her? Is that useful? Yeah, because now you're saying we can subtract. Awesome, way to think of that. So we have 2 to the x squared. When you divide the same base, you subtract. So that's x squared minus 3 equals base 2 to the 2x. That's a true statement. So now you have x squared minus 3 equals 2x. You'd say I have a quadratic. To solve quadratics, we get it set equal to 0 and solve by factoring. So it factors to be x plus 1, x minus 3. Therefore, my 2 solutions are x equals negative 1 and x equals 3. Awesome. Okay, I think we're good with solving. Get them as the same base. Okay, these are the last pieces here. It's the story problems, which are the easiest ones of the whole bunch. So let's read it. It says, from experience, the manager of a crisis helpline knows that between 3 a.m. and 5 a.m., calls occur at a rate of 3 calls per hour. The following formula can be used to determine the likelihood that a call will occur within t minutes of 3 a.m. It says, what is the likelihood that a person will call within 5 minutes of 3 a.m.? What would I do? Plug in a 5 into the equation and use your calculator to calculate it. Is that hard? No, it is not. So you would say 1 minus e raised to the negative 0.05, and then it said the time of 5. Oh wait, is it the time of 5? Yeah. And you would literally calculate it. That is not hard at all. Do you want to calculate it and see what it comes out to be? So this is, let's calculate it, because likelihood is a probability. So our answer is going to come out a decimal, which is a percent. Likelihood means percent likely to happen. So what decimal do you get? Anyone get a decimal? I don't think it should have come out negative. 0.22? Did anyone else get that? So I have more than one person? Awesome. So we got 0.22. So that's a 22% chance of likeliness to happen. Does that make sense? Okay. Easy. Let's read one more. It says the half-life of thorium-227, that's just a name, that's not mathematically anything we plug in. It says the half-life of thorium-227 is 18.72 days. Suppose that a researcher possesses a 10-gram sample. The amount A of thorium-227 after T days is given by this formula. How much of the sample is left after 10 days? What would I plug in? 10. So it would be 10 times the half raised to the 10 over 18.72. Calculate it. Does that make sense, everybody? That's not hard, is it? No. Yes. I mean, for these type of problems, that's usually what you will see. But once again, with story problems, it'll always be related to what we've learned. So it'll be plugging in something. You know what I mean? This is exponential, so do you see how those are all exponential? Okay, this is the last thing. Write it down. This is really the last example. Okay, so here's the formula for interest. Like if you put money in the bank, this is an interest formula. So it says the amount A after T years due to principal P invested at an annual interest rate R compounded N times per year is this formula. So from this formula, we got to say what everything is. A is the amount in the end after you've invested. P is the put down amount, or they call it the principal. Obviously, if we're going to gain some interest, you have to put down some money in that account, right? You're not going to be able to get interest unless you put in some money. And then this 1 plus R. R is the rate. Now remember when we get, normally, here's the thing. For you advanced thinkers, think about this. Normally when we gain interest, like if you're getting 20% interest, remember how we have to do 1.20? With this one you don't. Here's why. They have built into the formula the 1 already being added. Do you see how this 1 is already there? That's the 1 with the rate that we normally have to add by ourselves. Does that make sense? So our interest rate we'll put in exactly as we see it. So if it's 8%, you would use 0.08. You wouldn't use 1.08. They've already taken care of the 1 in the formula. Okay? Now N is the number of times you get interest in a year. The number of times it compounds in a year. Compounds means gains interest. Per year. And then T is the time in the account. So let's say that you get interest every month for a year. Our N would be 12, because that's 12 times you get interest in 1 year. Does that make sense? So let's read this problem. Suppose you deposit $3,000 into a Roth IRA today. So wouldn't that be our put down amount? So you put in $3,000 in. Then we have 1 plus, what's our rate? Let's read. It says, determine the future amount of a deposit if it earns 8% interest compounded quarterly after 10 years. So our interest, our R is 0.08, isn't it? Our N is the number of times we're gaining interest in a year. Compounded quarterly. 4 quarters in a year. 4 quarters in $1, right? 4 times. You're getting interest quarterly. That means 4 times. So you'd say divided by 4, raised to the 4 times the time in. So 4 times 10. So then you just type it into your calculator, and you would see how much money you would earn after 10 years if you got interest 4 times a year for the 10 years. So I would make sure I could actually type it in right. If it was me, I would type it in and make sure you get the correct answer. I get that we will have, after 10 years, $6,000 $9,624.11. So that is the end of the lesson. So you will now do evens or odds for 9.2. You know the drill.